start like I usually do and mention something about Turan's theorem. So let me start by just recalling some results about graphs. So I won't define the extremal number. You guys are familiar with it. So as you know, the extremal number of a triangle, this is something like n squared over 4. This is Montel's theorem. And and let me remind you what the extremal number of the 4 cycle is. So extremal number of C4. Asymptotically, it's n to the 3/2 over 2. And this was proved by Berge, and Josh. Some other preliminary things. Let me remind you what is the extremal number of a C4 if we also insist that the graph is bipartite. So let me write it like this. And C4. So now all of a sudden this factor of 2 drops down to 2 root 2. So this is due to Kuvari, Shosh, and Turan. And okay, let me finally say that in the graph case, so it's still an open problem, an interesting conjecture. What is the Turan number if we forbid both a triangle and a 4 cycle at the same time? So this is still an open question of Erdős. So it's conjectured by Erdős and Szymonovic that if we forbid a triangle and a C4, it should behave as if we were in the bipartite case. So it should be hence a 3/2 over 2 root 2. But we don't know. So, and one more thing. If instead of, say, C4, if we forbid some arbitrary even cycle, then we have the result of Bondi and Szymonovic at EX and C2K. Well, we know that this is, we don't know exactly what the order of magnitude should be, but there's an upper bound of the form n to 1 plus 1 over k. This is Bondi and Szymonovic. So that's just a reminder in the graph case. For the rest of the talk, I'm going to focus on hypergraphs. I just wanted to mention these results. So in the hypergraph case, there's various notions of a cycle that we could have. So there's the idea of a linear cycle. This means that hyperedges, we order the hyperedges along in a cycle in such a way that each one intersects the next one precisely one vertex, and there's no auxiliary intersections. There's a notion of a tight cycle, cycles in the trace, and various notions like this. But for today, I'll talk mostly about Berge cycles. Okay, so what is a Berge cycle? So definition. So a Berge cycle of length, let's say k. Well, I'll just think of it informally as a sequence. So it's a sequence in a hypergraph. So I'm taking hypergraph elements. Let's say V1, E1, V2, E2, VK, EK, such that so for all I, Vi and Vi plus 1 are in the ith edge. Let's say mod k. So we could write it this way, just to denote that it. So yeah, you're right. It's conventional to denote a cycle this way, just to indicate that it kind of wraps around, and maybe a path we denote without the vertex at the end. But yeah. So in a sense, this is the weakest, kind of the weakest definition of a cycle. Almost.
We also want these vertices to be distinct. And
Yeah,
edges.
yeah, that's important. That's important. Yeah, you're right. So the VI are distinct, and the hyperedges EI are distinct. Yes. Yeah, very important. Thank you. Yeah. So this is kind of a very weak notion. So I don't know. Example. Let's say we're in a 3 uniform hypergraph, and that's a hyperedge, and then maybe we consider the edge from this vertex to this one, and then we could take some other hyperedge that looks, say, like this, even if it intersects the previous hyperedge in 2, that's fine. And then maybe we have a hyperedge, let's say like this, with a new vertex. And then we consider this edge. And then maybe we have, I don't know, say this hyperedge. Yeah. So this would be an example of a 4-cycle in the Berge sense. So it's a very weak way. It just means that that we can find a 4-cycle in a way that we assign a unique edge to each hyperedge, but we don't care at all about how the hyperedges intersect outside of these defining vertices, or if they contain some other defining vertex which we're not currently considering. Okay, so that's a Berge cycle. I won't define a Berge path, but it's completely analogous. Okay, so what is known about the extremal number of Berge cycles? So let me start by mentioning in the triangle case. So the extremal number, and I'll just write a b in front to denote Berge cycle of the triangle. This was proved to be n squared over 8 by Győri.
So now C3 is like a set of possible Berge cycles, or
Yeah, you can think of it that way. Yeah, I haven't been incredibly formal here, but yeah, you can think of it as actually a Berge cycle is a collection of hypergraphs, and yeah, so this is like n comma a forbidden collection of specific isomorphism classes of hypergraphs. So yeah, if I forbid all the Berge cycles which are triangles, then Győri proved that n squared over 8 is the bound. And the construction is quite simple. I just take, say I take a graph with n over 4 on one side and n half vertices on the other side. And I totally connect it, so it's a complete bipartite graph. And then I take all the vertices on one side and I double it, so that each thing that was an edge before becomes a triangle now. So I double all the vertices on this side, so that I get n over 2, n over 2. And it's simple to check that by doing this I don't introduce any triangles. And since I started out with n squared over 8 edges, in the end I also have n squared over 8 edges. And Győri proved this was sharp. So, okay, so let me write a 3 here to denote that I'm talking about the 3 uniform case. So actually, Győri's result simultaneously also proves the 4 uniform case. So if we consider Berge triangles in a 4 uniform hypergraph, he proved that this is n squared over 16. And the construction is basically the same, except now I start with n over 4, n over 4, and I double on both sides. So double on both sides to get n half. Okay, so that's that. And then, okay, you can ask what happens if we go beyond that, if we consider EX 5 in C3. And actually, this already drops to a little O n squared. So actually, we proved with Methuku and Danny Gross that any graph you consider, if you take the uniformity high enough, it will drop down to little O n squared eventually. is close. Okay, so that's about triangles. Let me mention what happens with higher cycles. So a sort of analog of the Bondi-Shimonovich theorem is true for Berge cycles. So EX and so I say the 3 uniform case. Actually, this is true for the R uniform case, but mostly I'll be interested in the 3 uniform case here. So let's say Berge C2K. Actually, both the Berge C2K and the Berge cycle with 2K plus 1 vertices, and the C2K plus 1. Both of these are upper bounded by n to the 1 plus 1 over k. This was proved by Győri and Lemons. So the behavior is a little bit different here, where unlike in the graph case where the odd cycles are all quadratic, in the hypergraph case for Berge cycles, actually, it doesn't matter whether we consider the even cycles or odd cycles, they both behave in this subquadratic way. Okay, so what about 4 cycles? So in the case of 4 cycles, EX, again, for the rest of the talk, I'm only going to be interested in the 3 uniform case. So let's say first that we don't just consider a 4 cycle, but we forbid also a triangle, and we also assume that the hypergraph is linear, which means we don't have 2 hyperedges sharing 2 vertices. Okay, but by our definition of a Berge cycle, what does it mean if 2 hyperedges share 2 vertices? This is a cycle of length 2 in the Berge sense. Yeah. So I can write, if I forbid the set BC2, BC3, BC4 of cycles, it's known that this is asymptotically n to the 3/2 over 6. This was proved by Lazevnik and Bustrade. And actually, interestingly, you don't need the full assumption here. You can also get rid of the not worry about the triangles, and it's still true. So if I have a linear hypergraph, so no 2 cycle, and I forbid 4 cycles, still the answer is n cubed over, n squared, n to the 3/2 over 6. So even without this, without caring about triangles, okay, that's proved by Ergemlidze, Győri, Methuku. But now we can ask, okay, what happens in the case where we just forbid a 4 cycle? So this is kind of the first, the next question to solve. We won't solve it today, only obtain some bounds on it, but this is the next natural thing. So what happens in the case of EX3 and BC4? Okay. So let me first mention the construction. So we know that, okay, so suppose we start with bipartite graph with n over 3 on this part and n over 3 on this part in such a way that we have no C4 between the 2 classes. So let's say no C4 in the graph sense, no C4. Then we can cite this result of Kuvare-Shoshin-Turan, which is asymptotically exact. And here we should just divide by a 2 root 2 factor. So if we start with this graph, so far we have, well, the number of vertices, which is not n, but it's 2n over 3 here, because I started n third. So I have 2n over 3. And I take that to the 3/2 power. And the Cuvier-Chauche-Turan results as I divide by 2 times square root of 2. Right? So if I do that, what I get is that this is n to the 3/2 divided by 3 root 3. So this is what we sort of conjecture should be the right answer for 4 cycles, but not what we can prove. Sorry, I didn't explain how to make the hypergraph. So I start with the graph with n third. How do I make the hypergraph? The same way as in the triangle case, just double one of the classes. So I just each vertex on the top is replaced with 2 vertices, and each edge before is replaced with a triangle. And it's so in the end I have something with 2n over 3 vertices up top, n over 3 downstairs, and you can check that this has no 4 cycle, no Berge 4 cycle. It has 4 cycles in the trace. It is if I look at the 2 shadow, if I look at the edges contained in hyperedges, I have 4 cycles, but they're not 4 cycles in such a way that I can assign a unique hyperedge to each edge. They're not Berge 4 cycles. Okay, so this is a lower bound. And what I want to talk about is the upper bound on this number. So what I'm going to talk about is the upper bound on Berge C4 of the form n to the 3/2 over square root of 10 plus smaller order term. Okay. So, okay, what to do here? So, I don't know if we'll get through the whole proof, but I'll try to get through what I can. So first, let me talk about some definitions which would be useful for us. So it's very useful when you're talking about these kind of questions to take the hyperedges and kind of decompose them into blocks of some kind. So I'll say that E and F, so suppose I have a Berge-cycle free hypergraph. I say that 2 hyperedges in it are in the same block. Well, if either the intersection of the 2 hyperedges is large, so it's at least 2, then I definitely want to call them in the same block. Or there exists a sequence of hyperedges, say E1, E2, ek. I don't really care about if these hyperedges repeat in this sequence. If there exists a sequence of hyperedges so that E intersect E1 is equal to 2, EI intersect EI plus 1 is equal to 2, and EK intersect F is equal to 2. So I can get to one hyperedge to the other by a bunch of 2 intersections with other hyperedges. So this is a decomposition of the hyperedges. So in other words, again, let me sort of skip defining things and just write that the edges of our hypergraph, this is a disjoint union across the blocks. So let me write B element of BH. These are the different blocks in H of the edge set of these blocks. So I can decompose the hyperedges in this way. Okay, so first let me just show something about the structure of these blocks. So I'll erase this. By the way, if there's questions, feel free to interrupt, because probably we won't get through the whole proof anyway. It's fine.
So you're not requiring EIs to be distinct or anything. So
I don't care. Yeah, it's okay. So it's just this. I'm just defining an equivalence relation on the edges. So this is a partition of the edge set.
could you say what the construction was again?
Yeah. So I start with the bipartite. So this is n over 3, C4 free,
Right.
and then I double one side.
I see. So you have a balanced C4 bipartite construction.
Right. Yes.
I get the end.
Yeah, and this is known to be the optimal bipartite C4 free construction. So if you want to beat this somehow, you have to find some. Well, you have to do something else. Yeah.
On this point, for which level of K, some construction is known, which matches the best lower bound. Sorry, best upper bound. Like for which level of K, the exponent matching exponent lower bound upper bound.
In the
C2K, like this, like for Berge-cycle 2K or 2K plus 1.
I think nobody has considered C6s really. So yeah, so classically in the graph case, it's C4, C6, and C10, in which there's matching orders. Yeah, I haven't seen a matching. No, it must, right? You can do the same. You can do the same thing. We can start with a C6 free graph and make it bipartite. I don't know what the optimum bipartite C6 free graph is, but do that, and then you can do a doubling on one side, and the result will be Berge C6 free. So yeah, so it's the same. Anytime you have the construction in the graph case, you also have it in the hypergraph. Okay, so let me first say something about the block structure. So claim 0. We'll see what claim we get to. So blocks are of one of the following two types. Let's say of form type 1. It's not complicated actually. Type 1 just means that I have some hyperedge, and I'm just going to say this out loud because there's not time to write it. I have some hyperedge, and there's some other hyperedges hanging off of it, but they only use one pair of vertices here. They don't use two different pairs of vertices. So they all hang off and they go to a new vertex, and they don't. So this is, no, what am I talking about? This isn't type 1. Actually, no, I do want to allow this. So I start with some hyperedge, and then I have other hyperedges hanging off of it, but their third vertex is distinct for each hyperedge which is hanging off of it. So this is type 1. Or type 2, let me just write K4, 3, minus. So I just take 4 vertices, and I have 3 of the hyperedges in them. And this is what I call type 2. And that's it. So in this, if we're Berge C4 free, then the blocks as defined here will be one of these two types.
Under that assumption.
Under the assumption we're Berge C4 free. Yes. Okay. So I won't give a super formal proof of this, but I mean, okay, we can think about it. Suppose we have suppose we find already the complete graph on 4 vertices, missing just one edge. So let's say this is the edge which is missing. Now, what would it mean to keep going with the block? So we have these 3 edges, and we're just missing this one. So if we keep going, well, we could have something like this. But sort of the worst case is if we have something which keeps going from here. So we have some edge which intersects the 4 vertices in 2, and it goes to some new vertex. Okay, but how do I find a Berge C4 in this case? Well, let me call this vertex 1, 2, 3, 4. And I will find an edge So I will look at hyperedges avoiding 1, 2, 3, or 4. So I don't have the hyperedge avoiding 4 available to me because I say that that one's missing. But I can use the other 3 hyperedges to find Berge C4 here. So how will I do this? Okay, so I need some hyperedge which contains 1 and 2. What can I do for that? I'll take the hyperedge that doesn't have 3, and that will make an edge here. How can I get an edge from 1 to 4? I can take the hyperedge which doesn't use 2. So let me write like this. How can I get from 4 to 3? I'll use the hyperedge which doesn't use 1. Right? Because I had all 4 hyperedges available to me, but I didn't have the hyperedge which didn't use 4. So this means doesn't use. Okay. Okay, so what did I use? So to get from 1 to 2, I used the hyperedge which contained 1, 4, 3, 1, 4, 2. So it did not contain 3. To get from 1 to 4, I used the hyperedge which contained 1, 4, 3. To get from 4 to 3, I used the hyperedge which contained 2, 3, 4. Okay, and all I've written here is which vertex was missing from the hyperedge.
Actually, I'm confused with
Yeah.
the diagram.
Yes. So what I'm trying to show is if we're in the case where we have a type 2 edge, if we're in the case where we have a K43 minus, then I want to show that we can't continue the block in any way, that we're stuck in that case.
If you contain it, then it is.
Then we're done, yeah. And all I say is, okay, suppose we have some edge hanging off. In a sense, there's 2 cases, but this is the worst one, that we're something like this, and we go to a new vertex. And now I'm just defining for you, or showing you where we find Berge C4 in this. To argue that we cannot keep going if we have a K43 minus. And I just said that, okay, if we have this, then I have all the hyperedges except for the one which is only missing 4. But then I can construct, using the red edge plus these 3, I can make a Berge C4. That's the point. Okay. So that's kind of case 1, that we have a type 2 edge. Case 2, if we don't have a K43, let's say.
Sorry,
Yep.
the type 2, I don't see the other case. Why don't we have the other type of edge?
It's another case to consider, but I just considered this one.
Just want to skip that case.
I'm going to skip that case because if you want to see it, I can show it.
You can assume that the red edge does contain 2 and 3 without lots of generality.
Yeah, that is fine. But why don't we have one which contains only one of those?
It could be 3 and 4, for instance. It has to be 2 of these because a block is defined to be 2 intersection, 2 intersection, 2 intersection.
Right.
So if the block continues, it has to 2 intersect this 4 set.
Yeah.
But you're right, there's one other sort of case to consider, but really that's an easier case. And not that this case is hard. Okay. So, yeah, so let's look at type 1. Okay, maybe I just hand wave this slightly. So if it's true, okay, I'll just kind of say this briefly in words. If it's true that for all hyperedges, we only have one hanging edge. We only have an edge hanging off of one pair of vertices, like this. Well, if that was true, then certainly we can't continue it with a new edge, because then this triangle would be an edge where there's 2 pairs of vertices with an edge hanging off it. So we may assume that we have an edge with 2 pairs of vertices, each with an edge hanging off it, something like this. Okay? Suppose we do. Now suppose we want to keep going. If we have another edge hanging off like this, let me show you where the Berge C4 is. Well,
So sorry, I was confused earlier. Now you have 2 edges with just intersection 1.
Well,
White.
I mean, yes, two edges hanging off this will always have intersection 1.
Yeah, so they are not in the same block.
Well,
They are-
there's
They are in the same block by the sequence. So this edge with this edge and then this edge. So they're in the same block.
So it's like that's the adjacency relation, right? Then you take this. Right?
Yes.
Why couldn't that have been in the other case with the
So all I argued so far was that if we have a K43, then we're stuck. We can't keep going. And now I say suppose no K43, and I want to argue that we don't have anything beyond structure.
So sorry, getting to the K43 case.
It's K43 minus, yeah.
Yeah. So why can't we have an edge which has intersection 1 with that and is then connected with such a chain?
Well, there can be edges like that, but I'm looking at what the block looks like. So if there is an edge like that, it won't be part of this block.
Why not?
Well, because to find additional edges in this block, we will need a sequence of edges to get from these to that one. Which means that we have to leave this 4 set at some point with an edge coming out that uses 2 of these 4 vertices.
And those edges already need to be in the block as well? Or?
Yes. So you're saying what if we have a thing where here's the 4 cycle and now we find some new edge coming in like this, right? Your picture in your head is something like this, right?
Yeah.
But in order to get to this, we have to have some sort of sequence of edges to get to this one that comes back. Because we're so okay, it's kind of strange. So basically, all I say is that once we have 2 edges like this sharing a vertex, we don't have any more external edges because this will yield a C4, Berge C4. So let me call this hyperedge 1, hyperedge 2, maybe hyperedge 3. And okay, I'll call this hyperedge 0. Then I have a Berge C4 because I can use 3 to go like this. I can use 2 to go from here to here. I can use 1 to go from here to here, and then I can use 0 to go back to there. So this is okay. So it is a little bit fast, but this is more or less shows the types like this. Okay.
So for type 1, you can really have 2 different groups of edges, or a pair of edges like this, and a bunch of and a whole bunch hanging off of each of these.
That's right. That's right. Yes. Actually, we're allowed. I didn't really draw it, but I also allow in type 1 that we have 3. I don't even know if that's. Yeah, I guess it's possible also, but that's not. It's also included that we use all 3 pairs. Okay. So now let me just mention the key definitions that are in this proof. Okay, so we have our hypergraph H. I'll denote by this. This is the 2 shadow of H. This means it's a graph on the same vertex set as H, but we have an edge in the 2 shadow. So say our edge is in the edge set of the 2 shadow. If and only if there exists H such that E is a subset of H, which is in the hyperedge set. So the 2 shadow is just the projection down to the 2 element sets from the 3 element sets. I mean, it's not projection, but taking all the 2 element subsets, which are subsets of some hyperedge. And now the idea of the proof is to kind of double count the, as in the original Kaveri-Shoshtran proof, to kind of double count the 3 vertex paths, cherries as they might be called. So there's 2 definitions I'll need here. First, let me say something about C4s. So this is going to seem like a little bit contrived for a second, but maybe we'll see why. So a 4 cycle in the shadow is called rare. So here's a 4 cycle, x1, x2, x3, x4. If we don't have a pair of hyperedges which intersect in the diagonal of this force cycle. So let me just draw 2 pictures. So if we don't have 2 hyperedges, hyperedge 1, hyperedge 2, whose intersection is the diagonal of the force cycle, and we also don't have the other pair. So, and no, this way, hyperedge, hyperedge. So we don't have either of these. That's a rare force cycle in the 2 shadow. Okay. And last definition, is this clear? So this force cycle is a thing in the 2 shadow, but it's called rare because of it doesn't have. There's not 2 hyperedges in the original hypergraph, whose intersection is precisely a chord in the force cycle. If we don't have, so we, yeah, you're right. Okay. Fine. Or, yeah. Sorry, thank you. So if we don't have either of these. We don't have this.
Is there some rotation?
Well, I mean, the difference is just. Yes. Yeah, it's symmetric. Okay, so we don't really have to say both. So we don't have a. There's not 2 hyperedges which intersect in the chord of the force cycle. Then it's rare. Okay. Just a definition. Maybe we'll see why we need it. Okay. And last definition. So as I said, the idea of the proof is to double count 3 paths, 3 vertex paths. So 3 path, I always mean 3 vertex path, is good. Okay. I know Pascal doesn't like good for this, but 3 vertex path is good. Let's say a 3 vertex path x1, x2, x3 is good, and there's 2 simple conditions. 1, I don't want it to be a hyperedge itself. So x1, x2, x3 is not a hyperedge. So I don't get this path in some cheap way by just having the hyperedge. And 2, there does not exist some 4th vertex which completes it to a rare cycle. Okay. And that is what we need. Okay, still okay on time. So is it clear what a good path is? So this is a object of the 2 shadow. So the goal of the proof will be to upper and lower bound actually all of the 3 paths, not just the good ones, but the goods will be a useful tool to bound on their own. Okay, so okay, let me move on. Okay, yeah, I'll include some other definitions. So very simple things. So d of v, this is just the hypergraph degree of a vertex v. D sub SV, this will be the degree in the shadow. Okay, strange. D EX V, this will be the degree in the shadow, which is in general sometimes bigger than the degree in the hypergraph itself. So it'll be this minus this. And last but not least, the block degree. This will equal the number of blocks which contain V. Yes,
So is dx allowed to be negative?
it could be potentially, but it won't be. Yes. Yeah. Yes. Okay. It won't be due to the block structure, basically. That if you so the idea will be to look at the blocks individually in lower bound dex, or the sum of
I
dex.
see. Cool.
Yes.
So when you take a shadow, you make a simple graph, right?
Shadow is simple graph. Yeah. Okay. So let's see. So some claims I will skip in the interest of time, maybe. Prove one of them at least. Okay, so for instance, one claim. Okay. So if I take two vertices in the vertex of the hypergraph, there are at most 2 3 paths. Let's say A, B, I, B, such that A, B, I, B is not a hyperedge in the hypergraph. So this is one of the two conditions of being good. So, and so this just says that if I look at the shadow, there's only 2 3 paths, let's say, in shadow of H. At most 2 3 paths between them, which are not trivial 3 paths in the sense that they just use a hyperedge to be a 3 path. Okay, so maybe just so I can prove something, at least I'll explain how this proof goes. Okay, so suppose by way of contradiction, I know there's debate on whether we should call it this or what. Okay, so suppose by contradiction that we have 3 such paths. This will give kind of a flavor of some of these items. So V1, V2, V3 between A and B. This is V2 shadow. So suppose we have 3 things like this. Okay, so this edge in the 2 shadow must come from some hyperedge. And in fact, we can find a different hyperedge for this one and this one by our assumption that A, V, I, B is not a hyperedge. So let's call this E1, E2, E3, call it F1, F2, F3. So what do we know? So in particular, EI does not equal Fi for any I.
Why are E1 and E2 different?
They're not necessarily.
Okay.
Yeah. So I just claim right now that EI is different from Fi.
Yeah.
Okay. And also EI is different from Fj for I not equal to j. And the reason for this is cardinality, that otherwise I'd find 4 vertices, and I'm in a 3 uniform hypergraph, so that's too many. Okay, so some of these EIs could really be the same. Okay, if everything is different, then I clearly find a Berge C4 in this picture. So let me assume that some of these are the same. So suppose, let's say without loss of generality, that E2 equals E3, E2 equals E3. So let's assume this, otherwise we're done. Now, we know that F1, it can't be that F1 equals F2 equals F3. Because if that's the case, that's 4 vertices in the hyperedge. So F1 is different from either F2 or different from F3, right? So we know that F1 does not equal F2, or F1 does not equal F3. One of these is true. Maybe they're both true, but at least one of these is true. Okay, so we can again assume, without loss of generality, that F1 does not equal F2. It's a completely symmetric thing in the other case. So we assume F1 does not equal F2. Well, okay, then we're done already, because we have A, and then we use E1 to get to V1. then we use F1 to get to B. And now we know that F1 is not equal to F2, so we can use F2 to get to V2. Or in the symmetric case, F3 to get to V3. And then we can come back because we know that if E2 equals E3, then E1 does not equal E2, right? So then we can come back and use E2 to get back to A. So that's, yeah. So that's how something like this is proved. Okay, let me switch points. Okay, now, okay, maybe I shouldn't have erased the definition of rare, but fine. So here is a key bound. Okay, we're up to claim 2. Claim 2. There are at most 6 times the number of hyperedges. Rare 4 cycles. Rare or not rare? Not rare 4 cycles. Rare or not rare? Rare. So most that many rare 4 cycles. Shadow. Okay. So this is going to be proved using claim 1. So again, assume that there's 7, let's say. Well, okay, so maybe before this. So every 4 cycle in H shadow, definitely there should be some edge from the hypergraph contained in that 4 shadow completely. Sorry, in that 4 cycle in the shadow, there must be an edge from the original hypergraph contained as a vertex subset of that 4 cycle, because otherwise that 4 cycle would just immediately be a Berge 4 cycle. Yeah. So in a sense, the idea is to represent all of the rare 4 cycles by using the edges of the hypergraph. So we show that we take an edge of the hypergraph, and it can only be contained in some bounded number of rare 4 cycles. That's the idea. So we take some hyperedge, say A, B, C is a hyperedge. So this claim will be done if we could show that this can't be in too many rare 4 cycles. So suppose it is in 7 rare 4 cycles. Okay. So what does this look like? So we have I don't know how we want to call it, A, B, C. Now, what does it look like to be in a 4 cycle? Well, we can kind of think of this like a triangle, and then to be in a 4 cycle means we replace this edge, and we get a 4 cycle in this way. So basically, if we're going to make a 4 cycle and it's going to contain A, B, and C, it's going to have to look in one of these 3 forms. So deleting the corresponding edge and making a 4 cycle. These are the 3 different ways in which V can play the. I mean, if you prefer to think of it in terms of permutations, this is like we have four elements in the permutation. So there's 3 factorial cyclic permutations, but we don't care about flipping. So it's like 3 different possibilities. Okay. So if we have 7 things by pigeonhole, we have 3. We have 3 of one type. So we have something like B, C, A, and then we have 3 cherries hanging off one pair. Yes, but the point is we assume that a good. So these three have to be. What is the point? So it's a rare cherry. So this is a hyperedge. So it cannot be that these red V's are hyperedges because we are looking at rare 4 cycles. And in a rare 4 cycle, we don't have the two diagonals intersecting in the chord. Right? So these are sort of distinct edges. But now we go back to claim 1, which says that we don't have 3 of those. We can have at most 2 of those, and this gives a contradiction. So in a sense, so here we bounded that there's at most 6E rare 4 cycles. And then that gives a bound on the number of not good 3 paths. So the number of, say, not good P3. Well, on the one hand, we can have a bad 3 path by it living in an edge. So we can have 3 times, so a hyperedge can contain a 3 path. So that's one way in which it can be bad. But we can also have a 3 path which is not good because it has a 4th vertex which completes it to a rare 4 cycle. But we've seen that we only have 6 rare 4 cycles. So naively, we could write a 4 times 6 E of H. Actually, you can write a 3 here instead of a 4 if you want, but it doesn't matter. So in other words, we can bound the number of 3 paths which are not good because a 3 path is not good either because it lives in an edge or because it's part of a rare 4 cycle. And we have a bound on a number of rare 4 cycles, and that gives a bound on the number of not good 3 paths. Okay, so what I have 2 minutes left. I will just mention what we do about the good 3 paths. I will prove it. So again, we're going to apply that first claim. So the number of good P3s is bounded by, so remember a good P3, there's no hyperedge containing the P3. So there must be, we must use distinct edges for the 2 edges in the P3. So for any pair of vertices we take, we can only have 2 good P3s containing those as endpoints. But this isn't good enough. So the way that we refine this is actually we can subtract off this from this something that we look at the blocks. Sorry, you could just think of it as sum over V of the block degree of V choose 2. And so basically, rather than getting 2 different good 3 paths for each pair of vertices, sometimes we only get 1. And the reason we only get 1, if you kind of think about it, here's a vertex V, and suppose it belongs to 2 different blocks. So say block on the left, block on the right. What we could show is, it's not that hard to show, that there's at most 1 good 3 path between either of the xi's and either of the vi's. So in for each such v which straddles 2 blocks, we can reduce this number by 1 for each of these pairs. Yeah, so that's that. And then on the other hand, the total number of P3s is just equal to the sum of the vertices. Well, it's the shadow degree of V, choose 2. But as we wrote that, this is the sum of the vertices of the excess degree, which is d shadow minus d, plus the original degree, choose 2. And the rest of the proof proceeds by just bounding a sum of these things, bounding some of these things, and using some Cauchy Schwarz. So that's a rough sketch. Stop there.
high uniformity?
Maybe. Well, higher uniformity, I don't know. For 5 cycles, there is some bound known, but for Berge C4 and 4 cycles, so I will remark that, no, actually we don't know that. Yeah, so I guess we've talked about this before. It's kind of an open question on whether, like for Berge C4, whether we eventually get sub n to the 3/2 or not. This was, I think we tried this a bit. This is in the dense case. In the n squared case, we know that eventually it's little n squared by using some triangle removal and stuff. But in the sparse case, we don't. So, but we do know up until uniformity 9 at least, because what you can do. So Bustrelli, as I mentioned, proved that there's a 3 uniform hypergraph of girth at least 5. And what you can do is you can take each vertex in that and replace it with blow it up by a factor of 3. And if you do this, you will get a what is that? Yeah, that's a 9 uniform hypergraph, and it will have no Berge C4. So, and it will have order n to the 3/2 hyperedges. So the order n to the 3/2 is true up until at least 9, but we don't know if it fails already for 10 or not. We don't know anything about the constants for larger uniformity.
It's always monotonically decreasing as you increase the uniformity?
No. I mean, for a general graph, no, it's not. You have to think a little bit what the countersamples, but definitely it can jump around. Even the exponent and the power of n can jump as you go higher uniformities in general. But always, for any fixed graph G, it's always eventually little o n squared if you take huge uniformity.
Have people tried to attack this problem by using flag algebra? Is there some hope for it?
Yeah.
Like just mechanicalizing?
I mean, the thing about flag algebras is, to my knowledge at least, they're only useful in the dense case.
Oh.
So, for instance, maximizing C5s in a triangle free graph, you have order n to the 5 of those, so you can use flag algebras. But as far as I know, there's no real version of flag algebras that work if you're not expecting the highest power of n for the thing. Who knows?
Any other questions?
So you give it a go on, right?
I believe it, yeah. No evidence for it.
Is there some another definition of the hypergraph cycle?
Sure, yeah, things change a lot. Like if you forbid a linear cycle, then linear cycles behave kind of like the Ergemlidze theorem. So they're always, so in the 3 uniform case, it would be n squared. So a star, for instance. If you take a star in a 3 uniform hypergraph, this doesn't have a linear cycle because all the vertices contain the same fixed vertex. In tight paths, I don't know what the bounds are, but this was recently some people worked on this tight cycle case.
Any other questions? So, if not, let's take a